Element collecting is a hobby that has been gaining popularity among the science savvy, especially as many suppliers like Smart Element, Metallium, and United Nuclear, among others, have started making element samples more available. Some element collections consist of just high-purity samples of pure elements, but some are more diverse. Some people collect isotopes and chemical compounds as well. This is the nature of my element collection. I've collected both element samples of the pure isolated type, as well as interesting chemical compounds and isotopes. I made a video previously where I showed part of my isotope collection, the part purchased from the isotope supplier Isoflex, link in the description. Under normal circumstances, what you see on the screen right there is what my element collection looks like. What I'm going to do in this video is give an in-depth look of what I have in my element collection. I'm going to show each sample, talk about what it is, and where it came from. In order to do this, I'm going to take my entire collection out and lay all the samples flat on the desk, and then I'll go through each one. All laid out, my element collection looks much more substantial and intriguing. I'm first going to show you all of it by simply pointing the camera at different angles of the various parts so you can see it laid out clearly. And then I'm going to start going through each individual sample. The way I've organized how I've laid this out is the following. I put bigger things on both ends and in the back. So there are some bigger things here. Then I left some of the bigger, taller things in the back. And I've got some larger things there. Then I laid out all the assortment of little vials and test tubes of chemicals in the middle. Let's take a look at these test tubes from above. I've got everything from metals, compounds, enriched isotopes, and gases that I've got from all sorts of different places, mostly through the internet, but no one consistent source. This is what my collection has amounted to since I started collecting in 6th grade. I don't have large amounts of money, so it took quite a long time to accumulate this much. The first thing I'm going to go over is these 3 metal canisters here. The lids are to the right of them. They're not a consistent size, but the body of the containers are a consistent material. I personally machined these containers out of solid magnesium. And the lid of the first and third one, I'm also machined out of solid magnesium. The lid of the container in the middle, which is the smallest one, I did not machine out of magnesium. I machined it out of solid copper tungsten alloy. When the lid is on the container, it makes it quite top heavy because the body is fashioned out of light magnesium and the top is heavy copper tungsten alloy. And as you can see by the label, I normally keep 61.98 grams of erbium metal in here. These containers aren't just made out of interesting elements. They aren't just interesting element samples themselves, but they are used to store other interesting element samples. This is the chunk of erbium that it usually stores. I'm pretty sure I got this from Solution Materials LLC back when it was still called Gallium Source, but I bought it quite a long time ago, so I'm not entirely sure if that is in fact where I got it. In the front magnesium container that does have a magnesium cap, in fact a cap that screws on, I keep a chunk of lanthanum. The chunk of metal you see at the bottom there is, I can't remember how much, but solid 50, exactly 50 grams of solid lanthanum. You can see the oxide coating. It's under mineral spirits. This is the inside of the container, the magnesium container that normally holds the erbium metal. This is the inside of the container that I use to hold my gadolinium sample. It's very similar to the one that holds the lanthanum in that it has a solid magnesium body and a solid magnesium cap rather than just a solid magnesium body and a cap made out of a different material. The gadolinium chunk that I store in this container is right here. You can see it was broken off of some bigger piece. I'm not sure how, but it looks like the corner of an ingot. I think it's quite pretty. It is 59 grams of gadolinium metal that I got at Solution Materials over the internet back when it was still called Gallium Source. The foil-wrapped container you see lying on its side in front of the magnesium containers is white phosphorus, but it's light sensitive, so I'm not going to open it up and show you the sample, simply because I don't want the light to cause it to degrade. To the right of it, that sample right there, in the acrylic container, the one I'm pointing to, contains high-pressure xenon. In fact, so high pressure that if you cool it below 61 degrees Fahrenheit, it liquefies. I'll show you that later in the video. To the right of that, I have my collection of Spectrum Techniques radioisotopes, which I bought mostly directly from them, although one or two of them I may have bought through United Nuclear. The samples I have are the following: 10 microcuries of carbon-14, 1 microcurie of thallium-204, 1 microcurie of sodium-22, another 1 microcurie of sodium-22, a microcurie of barium-133, a microcurie of cobalt-60, 10 microcuries of cesium-137, and another 10 microcuries of cesium-137. Behind the Spectrum Techniques radioisotope samples, I've got a variety of vials with all sorts of substances in it. This one contains bis-1,5-cyclooctadiene nickel 0. This one contains turnings of terbium metal. This one contains radium paint from a clock that apparently used specifically radium sulfate. This here is a sample of deuterium oxide, or heavy water. This is a little chip of lutetium metal weighing 0.14 grams. This sample here is deuterated acetonitrile, so methyl cyanide, where all the hydrogen atoms are actually deuterium atoms. I've got a few different deuterated compounds because I had kind of a deuterium obsession in high school. This is deuterated lithium aluminum hydride, so lithium aluminum deuteride. And then on the other side you can see the name and logo of the isotope manufacturer, or at least supplier. I guess I don't know whether they manufactured it. Then here I have 98% pure concentrated sulfuric acid, but deuterated. So you could call it heavy sulfuric acid, just like you called deuterated water heavy water. I thought that was a pretty cool sample. I certainly wasn't expecting to ever see heavy sulfuric acid. Over here I have hydroxylamine deuteriochloride, so hydroxylamine hydrochloride except deuterated, so it's the heavy hydrogen version of it. This sample is a cylinder of cadmium metal that I turned myself. I bought the metal as turnings and then cast it into a cylinder and turned it on a lathe. This vial here contains one of the more toxic samples that I've got, 50 grams of pure thallium, which I also bought from Solution Materials LLC back when it was still called Gallium Source. This sample here is kind of an interesting one because it's an example of a compound with a cyclopentadienyl ion in it, specifically bis cyclopentadienyl hafnium dichloride. Now this vial here contains 2 microampules you see in there, containing milligram quantities of metallic cesium and metallic rubidium. I have a larger cesium sample, but sadly I have not obtained a better rubidium sample. I know where to buy them, but I have not spared the money to do so. In here I have a ruby laser crystal. I keep this as a sample of chromium, actually, because the color comes from chromium in the aluminum oxide. That's what makes it a synthetic ruby instead of some other synthetic gemstone. This is one of my favorite samples. It's 100 grams of thorium-232 4 nitrate pentahydrate, where the 232 refers to the isotope of thorium, thorium-232, and the 4 refers to the oxidation state. It's thorium-4 nitrate. I got this sample recently and I did an unboxing video with it. A thorium nitrate unboxing video. Link in the description. So that completes this section of my element collection. Let's move back and see what I've got over here, because I've got some interesting samples. The first one that I have that's worth taking a look at is this sample of molybdenum metal that I machined into a little rectangle. Then I've got an interesting lithium sample here, in the form of a highly reactive lithium compound called Lithium Diisopropylamide. This came from Sigma Aldrich, although it just says Aldrich on there. Anyway, it's pyrophoric, corrosive, air and moisture sensitive. I've got 25 grams of the solid material in here. I've heard it's one of the strongest bases in the world, although definitely not the strongest. I have, however, heard that it is the world's strongest non-nucleophilic superbase. Next to the lithium diisopropylamide, I have this old applesauce jar that's been repurposed to hold my calcium metal dendrites. Those are calcium metal single crystals. I thought they were cool because you usually don't think of calcium as a metal, and also I thought they were cool because usually even when you do have an element that you think of as a metal, you don't see large single crystals of it. Yet here it is, calcium metal single crystals. The metal cylinder below the molybdenum that I showed you earlier is a neodymium iron boride supermagnet. The next thing that I'm going to show you is this really long tube. It goes all the way over there. It's like 2 feet long. It's flame sealed at the other end and it's full of mineral oil, and the chips of metal you see in there are sodium metal. It's a 2 foot long sodium metal display sample. You can't just have a sodium metal sample, you have to have a 2 foot long sodium metal sample. Then over here I've got 2 more reasonably long vials leaning up against this small digital oscilloscope. The one in the front there is potassium metal and the other one is more sodium metal. In this desiccator here with a sock to keep it from rolling around, I've got a flame-sealed ampule containing 97% tertiary butyl isocyanide, the worst smelling compound I've ever purchased. It originally came, I think, from Sigma Aldrich, and it was 97% pure when I got it. However, the flame-sealed ampule wasn't perfectly flame-sealed, so I was smelling it and it was awful. So then I had to do the awful task of taking it out of the ampule and putting it in there. When I flame-sealed it, a small portion of it on the sides that was still sticking to the sides warmed a little bit and turned brown, and then that dissolved into the other tertiary butyl isocyanide. It's still 97% pure, or at least really close, because the amount of impurities that dissolved from the flame sealing process was so tiny. However, it was intensely colored, so it went from only slightly discolored to quite a bit discolored. Because I'm afraid of breaking it and how crazy awful it would smell if I did, I'm not going to take it out of the desiccator. I'm just going to leave it where it is. Over here I've got a test tube rack with an assortment of different samples. The two that I'm focusing on right now are more sodium metal. The one on the left looks basically the same as the other sodium that I showed you, but the one on the right I'm going to take out and get a better view of, because there's something unusual about it. Typically when I seal sodium in a vial, it at least forms an oxide coating as it consumes the residual oxygen inside the container. But for some reason, for more than 2 years now, the sodium has not tarnished. It's extremely shiny. I didn't do anything special in the way I sealed it, but for some reason it was extra effective and kept this sample of sodium metal extremely reflective. It's quite pretty, and I like having it in my element collection because it does a good job of showing just how shiny sodium metal really is. The vial of clear liquid next to the extra shiny sodium metal vial is tertiary butanol, the alcohol that freezes at a relatively high temperature. It's a liquid now because room temperature is a little bit above its freezing point, but it could freeze if it didn't get all that much colder in here. Then the vial to the right of that is, again, quite unusual, and I'm going to take it out and give you a better view of it, because it's worth talking about a little bit more. The golden liquid that you see above the droplet of red liquid, which you probably can't see in this view, but it's down there, and I'll show it to you with a better angle in a minute. The golden liquid is isopropanol with small amounts of disulfur dichloride dissolved in it from the degradation of the sulfur dichloride drop at the bottom that occurred before I got it sealed. If sulfur dichloride is not under some pressure of especially chlorine, then it will slowly decompose to emit chlorine and yield disulfur dichloride. But if it's sealed, then a pressure of chlorine will build up and it will stop decomposing. So before I sealed it, some of that degradation did happen, and it formed yellow disulfur dichloride, which dissolved into the isopropanol above it. The cherry red droplet that you see at the bottom of the vial is the sulfur dichloride, which I actually made by accident when, in one of my experiments, chlorine came in contact with sulfur. I captured it under some of the isopropanol that was also involved in the experiment to produce this sample here. To the right of the sulfur dichloride sample in this test tube rack is a strontium metal sample. And again, this one is interesting enough to warrant taking it out of the rack and getting a better view of it. At first, all it looks like is a bunch of heavily oxidized strontium metal under mineral spirits. But if you look closer, you might see that that piece in the front is unusually perfectly rectangular. And that's because I actually tried machining strontium once. I took an ingot of strontium and I put it in a milling machine, and under the spray of WD-40 to keep it from reacting with the air, I did in fact actually try machining strontium metal. It's now quite oxidized, but that rectangular prism is quite perfect, and it was machined that way on a milling machine. The sample in the tube to the right of the strontium that I just showed you is zinc hexacyanoferrate, and it's kind of a pretty color. I made it in a high school AP chemistry class. It's the sort of bluey purple powder that's in the water that I just shook around so it's suspended. I kept it because I thought it was a pretty color, but it's not some, like, spectacularly unusual material or sample or anything like that. I just kept it because I thought it was a pretty color. The bottle that I'm now showing on camera is a bottle containing 500 grams of phosphorus tribromide. The phosphorus tribromide just looks like water. It's not particularly interesting. But the story of how this sample got shipped to me is, I bought it from a chemical supplier in Korea. I don't remember what it's called, and I haven't been able to find them online anymore. They seem to not be there. And it was shipped to me in 3 steps. It was first shipped by a courier in Korea to some place where another shipping company carried it overseas. Then it arrived in the US and was handed off to another shipping company which shipped it from where it arrived at in the US to my house. However, I got this funny message from the supplier. They said after I'd bought it that they tried to ship it, but the shipping company in Korea wouldn't take it because they weren't interested in shipping something as nasty as phosphorus tribromide. So they said they solved this problem by taking off the phosphorus tribromide label and replacing it with a safe-looking label for a different chemical, and it made it through to me. That's their illegal action, not mine. I'm not liable for anything, but, it's kind of interesting that they chose to ship it to me in that way. The fact that they apparently are willing to do that kind of thing may have something to do with the fact that they don't appear to exist anymore. To the right of the phosphorus tribromide sample, you see a graduated cylinder with a ground glass cap in the top. I'm going to pull it out. The liquid you see is 3% hydrogen peroxide, and the white powder you see in the bottom is thorium peroxynitrate. The chemical formula is kind of complicated. I don't know if you can read it, but it's TH6 in parentheses OO10, and in parentheses NO3, and there are 4 of them. And by the way, when I said in parentheses OO10, I meant OO, the peroxide anion, was in parentheses, and then there's a subscript 10 on it, which means there are 10 of them. I made this sample when I took some dissolved thorium nitrate and poured it into hydrogen peroxide. It gelled up, and then eventually that gel settled to a more condensed form down at the bottom. Just to the right of the thorium sample that I just showed you, I have a bottle of what used to be quite pure chlorine that I created via electrolysis. At this point, it seems to have reacted partially with some of the water that I left in the container, and as a result the chlorine color isn't as visible, but it's still quite concentrated. It might not be pure, but it is concentrated enough that in the right lighting anyway, you can still see the green color of the gas. I think you can see it on camera right now. And because I made it myself and it actually lasted at least partially for a long time, I keep it in my collection, mostly just because it's a happy memory. In front of the thorium sample that I previously showed you, there is a aluminum canister with a chunk of sodium metal in it, weighing 100 grams. It's another bit of sodium I have. Then in the jar next to it, that black substance is lithium metal under mineral spirits, 60 grams of it that I took out of batteries. Then this sample right here is actually naturally occurring arsenic. Pure elemental arsenic, through some geological process, got deposited on a rock and formed sort of an arsenic geode, a part of which I have here. Now the only container on the perimeter that I have not discussed is this sample right here. Let's pull it up here so you can see it better. This is a fragment of Martian meteorite. I purchased it via eBay from one of the meteorite men who was selling it. It's not really an element sample or a chemical compound or like a pure compound. Obviously it is still made of compounds. but it is an interesting piece of material, so I thought it was worth having in my collection and also worth showing you. So now I have shown you all of the containers in the perimeter. So then the only thing left to cover, which is quite significant, are all the vials in the middle. I'm going to start on the left and work to the right. This first sample right here is green salt. It's uranium tetrafluoride, UF4. It's about 5 grams of it. And I thought it was one of the prettiest uranium compounds I'd ever seen. It's also one of the more famous uranium compounds because when uranium is used in industry, it sometimes passes through a stage where it exists as uranium tetrafluoride. I think it's especially common to use it when you're trying to produce the metal, because you can reduce the uranium metal out of the uranium fluoride with something like lithium or possibly magnesium. Next thing I have here is a vial of magnesium, which I'm not going to spend much time on because, well, I just showed you those magnesium containers. You've seen plenty of magnesium. And I've got black crystalline boron, some zirconium turnings, a piece of dysprosium metal, which is kind of interesting. You can see the crystals if I can get it to zoom right. You can see those crystals in there. And then next to it is a piece of scandium metal. It's a little square of it. And then a beryllium sphere and some other pieces of beryllium. Then a cylinder of lead. Now this cylinder of lead I machined myself after casting it. I bought a radioactive sample once and it came in a lead shield. I melted the shield down, cast it, and then machined it into the cylinder. And next door we see a zinc cylinder. Now this cylinder I also made myself. I got a bunch of pennies that were made before a certain key date, which I can't remember, that have pure zinc cores. And I melted the zinc out, casted it into a rough cylinder shape, and then machined it into a nice cylinder on a metal lathe. Here's a chip of thulium metal. And there's a chunk of yttrium metal. Hafnium metal. Hafnium turnings. Then this is some antimony chips. You can see they're shiny. Then here's a piece of tellurium. I think this is about 10 grams of tellurium. And then this is a vial of mercury, one of the more famous elements, of course. And then this is another lanthanide. It's a 5-gram chip of ytterbium metal. And here's some more calcium metal. Some nice crystals. I showed you those really big crystals earlier in the video. And then of course I have gallium metal here. It's a solid because we're below 85 degrees Fahrenheit. And then in here you can see a whitish powder under the water. That is uranyl peroxide. Then you can't see it because of the way it's turned, but this is a big chunk of dysprosium, 33.319 grams. Then I showed you that big chunk of gadolinium earlier. Here are some small chips of it. Then here's some heavily oxidized neodymium. The crystals are still in there though, but it's got a lot of oxide obscuring it. It's not the prettiest sample. Then here is some hydrated uranium trioxide. It's not as orange as it could be, but that's because it's hydrated. The less hydrate it has, the more orangey the uranium trioxide. Then here's some more radium sulfate clock paint underwater. Doesn't look that pretty, but it's definitely radioactive. It sets off my Geiger counter. And then in here is some clock paint also underwater. It's actually promethium clock paint. The radiation doesn't get through the vial. You have to take it out to actually get a reading. Okay, so now we can come over here and look at some of the smaller vials. This one's Barium Metal, the heaviest non-radioactive alkaline earth metal. Some chunks under mineral oil. Then I've got a smaller sample of thorium nitrate that you can actually see because the sides are clear. Then in here somewhere is a little chip of platinum. And some boron powder, tin, niobium, a little chunk of bismuth, and a bunch of americium-241 sources from smoke detectors. Then I've got some beautiful vanadium crystals there. They're little crystal clusters. It's quite pretty. Almost looks like those crystals of bismuth you see, except this isn't bismuth. This is vanadium. And then next door I've got indium chips, and that little vial inside the bigger vial plugged with the earplug, the left one, is 0.5 grams of europium sulfate. And that little vial is a tritium glow vial. And some tantalum wire. And then these colorful compounds here are uranyl acetate and uranyl nitrate hexahydrate. The acetate's on the left, the nitrate's on the right. They glow quite brilliantly under black lights, or at least the nitrate does. As you can see, when I hold it in front of a black light, it glows quite intensely. The uranyl nitrate does a good job absorbing UV light and converting it into visible light. I believe it's this compound that's used to color uranium glass, which glows similarly under ultraviolet light. This is a uranium glass bowl, the material I mentioned previously, and as you can see it glows similarly when exposed to the UV light. Just to the right of the uranyl nitrate I've got silver metal, and then here is a chip of natural abundance uranium metal. Just a little square of it. It's very thin. And then next to that I've got a vial containing another vial which is flame sealed and holds a gram of cesium. And next to it, that little chip of shiny metal is palladium. Then I have here 4 vials containing sodium metal chips, and then 1 gram of very oxidized thallium metal. See if I can show the chip. There it is, right by my finger. That's the chip of the thallium metal itself. Next door I have all of my Isoflex isotopes, which I made a previous video on already. And then I've got some metals from Smart Element. This one over here on the right is erbium. I showed that big piece earlier. Then lanthanum, I also showed a bigger piece of that. Then these are interesting crystals of samarium. And then holmium. Just next to the samarium to the left of it. And then this last one is chunks of cerium metal. These orange tubes here contain solid tetrachloroauric acid. They're antique vials. They say gold chloride on them, but the chemical formula just underneath that explains what they mean by gold chloride says chloroauric acid. So you can see it says chloroauric acid and then gives the formula of tetrachloroauric acid. So clearly when they say gold chloride, they don't mean what's normally meant by gold chloride, they mean tetrachloroauric acid. But it's interesting to see the solid crystals of it. I've got 2 vials, and also they came with this old sheet that talks about them. So it's kind of an interesting antique element sample. Then over here I've got an assortment of miscellaneous vials. I've got a tube of helium, then to the right of it a tube of 33% fluorine and helium. Then to the right of that is a tube of hydrogen. Then that metal rod in that tube is praseodymium metal from Thallium. The hydrogen and helium samples are also from Thallium. I can't remember where the fluorine sample's from. It may be from there or from a similar supplier. Then I've got a tube of bromine, 2 much bigger tritium glow vials. Then I've got some ruthenium in a flame-sealed tube here. Shiny. Then in these tubes, each are 1.5 grams of europium metal. That red rod there is a thin ruby laser crystal. And then this tube here is similar to one I've showed you already, a material I've already showed you. This is depleted uranium metal, a chip of it. I showed you the sample of natural abundance uranium metal that I had a little earlier. And basically they're the same chemically. The only difference is that it has 0.7% and this one, being depleted, only has 0.2% uranium-235. Then this is a tarnished copper metal rod. Then the glass looking rod next to it is an yttrium aluminum garnet or YAG laser crystal. I don't know what causes it to be pink. I don't know what trace element they added to make it pink, but the base material is YAG. Then there's a chunk of silicon that I've got here. Then this is a xenon discharge tube. And then finally, next to the xenon discharge tube, I had this copper bar, which I moved into better light. I took a copper pipe and melted it with an oxyacetylene torch that a friend of mine has. He let me use it. And then I also borrowed his milling machine to mill it into a nice ingot. This tantalum metal square was given to me as a graduation gift and is my only other tantalum sample aside from the wire that I showed you previously. For neon, I have 2 similar samples. I've got 2 helium neon tube lasers. This small one there, and then this much bigger one. It's not a pure neon sample, but it does contain neon, and it demonstrates one of its applications. When I turn the small one on, it looks like that. You can see the laser beam on my hand. It's not powerful enough to hurt or anything. In fact, more light is emitted just from the discharge tube inside than comes out in the form of an actual laser beam. When I turn the larger one on, it looks rather more dramatic, but ultimately it really is just a bigger version of the same thing. Again, you can see the laser beam on my hand there. It's a bit brighter. So then both of them together look like that. That comprises my neon sample, these 2 helium neon lasers. Earlier in the video I said that I was going to come back to the high pressure xenon sample. I said that if you cooled it below 61 degrees Fahrenheit, it would liquefy, and I was going to show you that. As the last thing I'm going to show you in this video, I'm going to show you the liquid xenon. This vial is under 942 psi, and that's the reason why it liquefies when it cools to not that cold of a temperature. You can see that there's a little bit of a line there. That's the liquid gas interface. And if I hold this for long enough, what'll happen is it will start to boil. But I don't think I've got a good way of showing the boiling. And it does the whole transition to a supercritical fluid like you often see with CO2, except this is xenon.